Binary search is faster than linear search, but it only works on sorted lists. So if our input is not sorted, we should either sort it first and then use binary search, or we have to use linear search, depending on the total cost. If there are multiple values we want to look up in a list, it often pays off to sort the list first and then use binary search. So let's say we're looking for 6 in this list. First, we look at the middle item. We can calculate the index of the middle item using this formula. Left plus right divided by 2. Here left is 0 and right is 9, so the index of the middle item is 4. We have 11 in the middle. The value we're looking for is 6. Since our list is sorted and 6 is smaller than 11, we definitely know that if we have a 6, it should be on the left side of 11, not on the right side. Because all the items on the right side of 11 are greater than 11 and we don't need to inspect them. This is why binary search is much faster than linear search, because in every step, we cut down the number of items we need to inspect by half. This is another example of divide and conquer algorithms. At every step, we divide the problem into a smaller problem. Now we repeat the same steps with the partition on the left side of 11. So here left is 0, right is 3, and the middle is 1. We have 5 in the middle, which is smaller than the value we're looking for, so we don't need to look at the items on the left side of 5. We're almost done. One last time. We calculate the index of the middle item. Here left is 2, right is 3, so the middle is 2. What do we have in the middle? The value we're looking for. So we have found 6 with only 3 comparisons, even though we have 10 items in this list. This is the beauty of binary search. Now let's do complexity analysis. What is the time complexity of this algorithm? You should know it by now. It's O of log n, because in every step, we reduce the size of our problem by almost half. And it doesn't matter if the target item is at the beginning or end of the list or doesn't exist at all. For all scenarios, the time complexity is O of log n. Now, what's the space complexity of this algorithm? You may think it's O of 1 because we don't need to allocate any additional space, but that's not quite true. Well, it depends. If we implement this algorithm using recursion, the Java runtime is going to store the recursive calls on the stack. So the amount of space we need on the stack is equal to the number of recursive calls. How many times can we divide this list into half? Log n times. So that's our space complexity if we use recursion. But we can also implement this algorithm using iteration. In that case, the space complexity will be O of 1. Now, does it mean the iterative implementation is better because it requires less space? Not necessarily. The extra space that we need in the recursive implementation is way smaller than you can imagine. For example, if we have 1 million items, log base 2 of 1 million equals 19. So we're going to find the target item with a maximum of 19 comparisons. So we need 19 recursive calls that should be stored on the stack. That's really negligible. The recursive implementation, in my opinion, is a bit cleaner and easier to understand, but that's subjective. Now, all that discussion aside, I want you to implement this algorithm twice, once using recursion and then using iteration. In the iterative implementation, we need 2 variables like left and right that determine the boundary of the segment we're inspecting. In every step, we update these indexes until the segment we're inspecting becomes empty. That's when our while loop terminates. So we'll spend 20 minutes on this exercise and then come back see my solution.